All right, if there are no questions, let's jump into some content. So today's lecture question is the first time we're seeing this restriction of not allowing the state to change in our program. So to that end, this lecture question, the next 4 lecture questions, and the next round of homeworks, which I'm working to release, we should see those soon, at least the documents. We're going to ban any changing state, which means the keyword var is going to be banned, and I may add some more restrictions to this for the homework. But the intent here is to force you into a recursive solution, and in general for these 2 weeks, force you into the functional programming way of thinking, to force you into using this approach, as opposed to the banning control flow to force you into the object-oriented way of thinking, changing behavior based on type. Now we want to go into this functional programming way. So the keyword var is banned for this lecture question, and the same restrictions apply as the state ones. If you have var anywhere in your submission, that's going to trigger the grader, and it's not going to grade your assignment. So make sure you're only submitting your code for this specific assignment when you submit. Make sure you're not submitting your whole project if you have all your code in one project. So with that in mind, what we want to write is a method that computes Fibonacci numbers. So if you've seen these before, like the question itself isn't meant to be too hard for your first recursive method that you're writing. Find the nth Fibonacci number. If you haven't heard of these, the Fibonacci numbers start with 1 and 1, and then each Fibonacci number after that is the sum of the previous 2 Fibonacci numbers. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on, to compute all the Fibonacci numbers. Now this has a pretty straightforward iterative solution. You would sum up, keep summing the values until you get to the index that you're looking for, but we want to solve this recursively. How do we solve this in a recursive way without using that var keyword? The loop, you would have an accumulator variable with var, and then you would iterate and keep summing into that variable using that accumulator pattern that you've seen in 115. So how do we accomplish the same thing with a functional way of thinking, a functional programming way of thinking, instead of that procedural way of thinking with the loop? So that's what we want to do here. And then just to define what index 1 and 2 are the first 2 ones. We'll start indexing at 1, and I won't test anything less than 1. You don't have to worry about the 0th Fibonacci number or the -5th Fibonacci number. I won't test for any of those things. Okay, so let's talk about sorting again, and we will talk about some runtime analysis. There won't be too much of this. I'll talk about a decent amount today, and then possibly never again for this semester. Maybe when we talk about data structures. But I guarantee you, CC 250, you will see this again. You will get healthy doses of runtime analysis in that class. That's pretty much the purpose of that class, is to do runtime analysis and getting your runtimes lower and designing data structures in a way to get lower runtime. So I'll give you a taste of it here. You had a small dose of it in 115. You'll get another small dose of it today. And then in 250, it's like the whole semester. You'll be talking runtime analysis and asymptotic analysis the entire semester, and actually proving your runtime analyses, proving that they're correct. So let's talk about it just a little bit today. We saw that selection sort was inefficient. It wasn't just a bad algorithm, but I also had a bad implementation of it. We'll talk about that in the next few slides. But how do we actually measure how good or bad an algorithm is in terms of runtime? And for that we use big O notation, which is an asymptotic measure of the number of steps an algorithm takes to accomplish what it's supposed to take. The term step can be a little ambiguous at times, so let's clear that up a little bit. Any basic, it's still unclear a little bit, but any basic operation, addition, subtraction, multiplication, logical and, any basic step that needs to be taken, anything that's going to go to our processor and need to be processed in constant time. So how many of those steps are taken throughout the run of our algorithm? And we want to measure this asymptotically, so we don't just want to say this is how many steps. It takes 532 steps to run this algorithm. That doesn't mean much to us when we're analyzing runtime, but we do want to measure the rate of growth of the runtime in terms of the size of the input. So what does that mean? We're going to have some input of size n. For data structures, for any data structure we use, n is going to be the number of elements in the data structure. And for our sorting examples today, n is the number of elements that we're sorting in that data structure. And we want to say asymptotically how many steps does it take based on that input size. So if, and then say that in big O notation. So for example, big O of n means that the runtime is linear in n, which is to say the absolute number of steps that this algorithm is going to take is some constant times n, and possibly plus another constant, or plus some other lower order term lower than n. So if the inputs, the runtime scales linearly with n, that's going to be O of n. If it scales quadratically with n, we'll have O of n squared, meaning that it's some constant times n, and then possibly plus some lower order terms for the total number of steps. And it doesn't matter what those constants are, is one of the big features of asymptotic analysis. The actual number of steps could be 1 billion times n plus 1 trillion, or it could be n divided by 15,000 minus 64, I don't know. But it could be any constants. N times 1 million and n divided by 1 million. Those are both linear runtimes. They're both O of n. We don't care about the constants when we talk about runtime analysis. Constants are a lot of times very important. A million times factor slowdown in our code is obviously something we'll care about. But when we're talking about asymptotic analysis, it's just not going to be important in these analyses. What we want to know is, as our inputs get very, very large, what's the difference in runtime? And that, in those cases, n versus n squared is significantly different than n time versus 1 million times n. Because what if your data structure is 1 million, then 1 million, actually that doesn't work because that's even, but what if your data structure is size 1 billion? Well, 1 billion squared is a lot different than 1 billion times 1 million. I'd rather take the billion times 1 million than the billion squared. So when the inputs get very, very large, that's what we're thinking about when we talk in terms of asymptotics. And often the inputs do get very large, because if the inputs aren't large, honestly, why are we even using computers? We use computers when we have lots of data, lots of numbers to crunch, lots of stuff to process. That's where we're really getting the advantage of having these very fast processors and lots of memory, is when the inputs are very, very large. So let's analyze our selection sort algorithm. I'll do a very quick analysis. We won't get too in-depth in this. Again, that's 250 will get you there. 331 also, you're going to do a lot of this. But let's just do a quick hand-wavy kind of proof to analyze the runtime of this. So for this loop that's in the box, I want to say how many times does this loop run? I have an input, so I'm going to measure everything in the size of this input data structure. So whatever the size of this data structure is, that's going to be my n that I'm going to measure off of, whatever this size is. This first loop iterates over every indice in this data structure, so this loop must run exactly n times. This isn't even n times a constant at this point. It's just n times. This loop runs n times. N is, of course, O of n times the constant happens to be 1. So O of n for this loop. And then I want to look at everything inside the loop. For each iteration of this loop, how much time does it take? Because I'm going to have to multiply those two runtimes together. This inner loop here, so the rest of this runtime is going to be linear or better. So I got to look at this loop here. However many times this loop runs, I have to multiply that by the n of that outer loop to get the total number of times the body of this loop executes. So if I look at this runtime, this one's a little trickier to analyze. I'm going from I to the size of the data. So when I is 0 for that first indice, this is going to run n times. So I can do a big hand-wavy thing and say, well, worst case, this is linear. Worst case, this runs n times, therefore it's O of n. And I kind of am going to say that. But this is not always going to be n times. For the next iteration, it's n minus 1. For some iterations, it only runs 1 or 2 times. So this isn't always running n times, but it will be O of n times. It is going to be an O of n runtime loop. And I'll show the math in a few slides just to make that a little more concrete. So this runs O of n times. The outer loop runs O of n times. So this gets us to our n squared runtime. We have n squared number of steps that are actually going to be executed. We have some steps, this call to the comparator, which has some basic steps in there. We're going to get some constant number of steps that are executed inside this inner loop, kind of, asterisk. So we have an n squared runtime for this entire algorithm. And then that asterisk is in this apply right here. That actually isn't constant time within that loop. So I actually have this apply method, which is going to take O of j runtime, where j is O of n. So I actually am going to get n cubed in this. I said I thought this might have been n to the fourth. After some more analysis, it looks like I do get n cubed, not quite n to the fourth, but still pretty bad nonetheless. So we do get n cubed with this implementation, which is worthy of noting that even if we do have an efficient algorithm, we might implement it in a sloppy way. If we're not choosing the correct data structures to implement our algorithm, we might actually end up with a much worse runtime than the theoretical runtime of the algorithm we're implementing. I have an n squared algorithm, but an n cubed implementation because I'm doing something terrible right here. And the reason why I want to do that is because we're going to talk about linked lists later in the semester when we get back from spring break, and I want to talk about why this was so horrible. So I can be like, hey, remember when I used apply and we got that n cubed? This is why, and we can talk about linked lists in that. This is going to take O of n time, though, to run. So assuming we didn't have that, let's just look at the steps of our loops. And I kind of hand-waved and said that inner loop, it's O of n, but it's actually not going to run n times every time. How can we just say that's O of n? So let's throw a little math at that. That inner loop is going to run n times on the first iteration of the outer loop, n minus 1 times on the next iteration of the outer loop, n minus 2 times on the next iteration, so on and so forth until it's 2 and then 1 iterations and those last few calls. But if we sum up this sequence, we get n squared over 2 plus n over 2. The leading order term is an n squared term, n squared times a constant. We're left with n squared times a constant plus some lower order terms, or otherwise known as O of n squared. With asymptotics, we ignore all the lower order terms. We only look at the highest order term, and we ignore all the constants as well. So this ends up being O of n squared. So this is an O of n squared runtime algorithm because it took some order of n squared number of steps to be able to do all the computation. Any questions on that one so far? All right, so let's do better. So we saw this really quickly in CC 115. It came and went really fast. It's one lecture of seeing merge sort, or not even a lecture, of merge sort, and we say it's O of n squared, n log n, n log n. But let's talk about why, and let's talk about how that algorithm works. We'll talk a little bit more about sorting, a little bit more about runtime. And then I want to shift focus onto the recursive part of merge sort. Merge sort does use recursion. That's what we're shifting into with the course. So let's talk about the recursion part of it, but let's talk about this runtime analysis first. So the algorithm, on a high level, this is what it does. You get an input list that you want to sort. If that list has either 1 or 0 elements, just return it. It's already sorted. This is what we call the base case of a recursion. It's some trivial input where the output is just so obvious we can just return it, sometimes without even computing anything. We just return the input. Or sometimes we have to compute some very little amount of work and then return that value. But something where it's very easy to compute the answer, some inputs, where it's easy to compute. If we don't hit our base case, and with merge sort, we're going to divide, we're going to hit our recursive step, our base case and our recursive case. Our recursive case is to split the list into 2 halves, call the algorithm itself recursively on each of those halves. The algorithm sorts lists, so that's going to return 2 sorted lists. And then I have the task of merging 2 sorted lists, 2 lists that are already independently sorted. I want to merge them into one list that's sorted, containing all of the elements in both of the lists. And of course, we'll talk about the recursive call once we're done with the runtime here. So if I have this input list, which is conveniently, just to make it pretty on the slide, a power of 2, size is a power of 2. So we have 8, and it's going to divide nice and even for the slide. So I have 8 inputs. I have an input of size 8, so I'm going to check. The algorithm's going to check. Is the input of size less than 2? Well, no, of course not. It's 8. 8's not less than 2. So we're going to divide this into 2 halves and run the same algorithm. Merge sort calls merge sort twice to be able to get the job done. So for each one of these calls, I'm going to run the same exact algorithm. This side, we're going to say, is this list size less than 2? No. Cut it in half, recursively call merge sort on each half. Okay, so for this half, size less than 2? Nope. So recursively call merge sort on each half. For this half, size less than 2? Yes. Now we finally got size less than 2. This recursive call can just return. Make this recursive call, that one just returns. Now we have the task of taking these 2 lists. Now we have the task of taking these 2 lists that the base case returned and merging them into a single sorted list. So this recursive call has the task of getting these 2 return values and merging them into one sorted list. So it has to tell that 1 goes before 51 to be able to get the right returned list from the recursive calls. Same thing over here. We get the 2 base case return calls. We get this list merged. And then this recursive call gets these 2 returns of size 2 and has to merge both those lists. So now this recursive call has the task of merging these, getting 1 where it goes, 19 where it goes, 51 where it goes, and 100 where it goes, and so on and so forth. The same thing happens on this side. So we get our top level call of the full list that we were trying to sort, gets these 2 recursive returns, and then has a task of merging those 2 lists into one overall list. So once we get to the base case, we can start returning back up the recursion and start merging those lists back together. So all said, the entire algorithm, not the entire algorithm, we'll talk about this merge method in a bit. That I haven't shown yet, we haven't talked about yet. We will talk about that. But the top level view of this algorithm is all right here. If the length is less than 2 of the input, just return it. Otherwise, find the midpoint. And I'm taking advantage of integer division here. If this list is an odd length, I want that just to be round down. So if I get a list of size 7, that mid is going to be 3. I'm going to get 3.5, but the 0.5 is truncated, and I'm just going to get the 3. This is one case where we do want integer division. I don't want to preserve the floating point values. So I get my 3 in that case. Split at is going to return 2 lists split at this index. So with a list of size 7, left would have the first 3 elements, right would have the next 4 elements. And then I'm going to make the recursive calls of merge sort itself. So I'm calling this method itself on the left and right. And I'm going to forward the comparator. Of course, we're still using the same comparator idea and the same type parameters that we used last time for selection sort. We're just improving the runtime of this algorithm. So we're going to forward those comparators to the recursive calls, sort the left and right. We're just going to assume that by the magic of recursion, that these actually did sort the lists, even though we haven't even finished writing merge sort itself. We're just going to assume that that worked. And then we're tasked with merging those lists together. I have 2 sorted lists. How do I merge them into one sorted list containing all the elements of both those lists? So let's look at the runtime of this. If we take a look at the recursive calls, and we want to ask ourselves how many recursive calls it took to get to our base case, which we want to ask. Let's take a look at the structure of this first. If we visualize this as what we call a recursive tree like this, what I want to ask is what happens each time we go down a layer of this tree. So if I start with this input of size 8, once I go down one layer, I'm going to have 2 inputs of size 4. If I go down another layer, I have 4 inputs of size 2. If I go down another layer, I have 8 inputs of size 1. So when I get down to the ith layer of this tree, my inputs are of size n over 2 to the I. And I want to ask myself, how many layers does it take to get down to my base case? So in our case where n was 8, it took 3 layers to get down to our base case, 2 to the third, 8. It's going to take that long to get to our base case, which is lists of size 1. So, and in general, it's going to take n over 2 to the I the size of each of the inputs at each layer, when that equals the size of our base case, what we're looking for to hit our base case and start returning, that's going to be, if we solve for I, that's the number of layers that it takes to get down to the bottom of our recursion and start returning up, which is going to be log n when we solve for I, solve this equation for I. So we get log n levels to this recursion, regardless of what n is, log n levels to this recursion. So if we can do, if our goal, which it is, n log n runtime, if we can merge these lists, if all the other work we can do, which was splitting into two lists, which we can do in constant time, and then merging. So if we can merge in linear time, we're going to get our O of n log n runtime. So that's our goal, is to merge these things in linear time. And this is where we start seeing, if you haven't seen this yet, the power of exponentiation, the power of logarithms. These are very powerful things in computer science, especially compared to our runtime. This has log n levels to the recursion. How long does it take to get down to my base case? Well, with 8, we don't really see the power. It takes 3 layers to get down to 8, 3 of these recursive calls going down. But if our input was, say, 1,000,000, what's that going to be? How long is it going to take to get to our base cases? Well, it's only 20 layers of our recursion. It doesn't blow up that much. These logarithms grow very, very slowly, and we can take advantage of that in computer science. Whenever we can get a log term in our runtime, especially when it's replacing an n term, that's a huge increase in efficiency. It's a huge increase in runtime. Log is the other side of that exponentiation. People say, it's become a common term these days, it grows exponentially. People say that when they don't really mean exponentially. In computer science, we actually mean exponentially. It's a very powerful thing to keep multiplying by a constant over and over again. We're usually multiplying by 2 over and over again. You multiply 2 by itself 30 times, you're at over 1 billion already. You can really increase, numbers can really blow up really quick when you have true exponentiation, exponential growth. All right, so we have to merge in linear time. So on the surface, it seems like we're faced with the same problem as the original problem. We have n elements, and we want to return a list with all those elements in sorted order, but we want to do it in linear time, which is impossible. We cannot sort using comparison sort in faster than n log n. It's been proven to be impossible. You just can't do it. So it looks like we're faced with an impossible task, except we can take advantage of the fact that each list independently is already sorted. So using this structure, now we can start getting a more efficient algorithm. So what we're going to do is start by looking at the first element in each list, compare those, whichever one comes first in the final sorted order, copy that to an output list, and advance that pointer by 1. And just keep comparing the two values that are being pointed at. If one of these pointers reaches the end of its list, copy everything from the other list over to the output. So we're going to start by looking at the first element. We're going to compare these two values. Which one comes first according to whatever comparator we're given. In this case, we're assuming just the less than is our comparator. 1 comes before 2, so I know that 1 is the first element in my output. Now I know that by a lot of transitivity here. So if 1 comes before 2, and this list is in sorted order, then I know 2 comes before all of these elements in this list. So if 1 comes before the first element in this list, it has to come before all these elements in this list. And there could be ties, but we're not too concerned. We'll break ties arbitrarily, either before or at the same spot as that. And I know this list is already sorted, so 1 already comes before everything after this. So by just that one comparison, I was able to effectively compare 1 with all n elements in both lists. Just with one comparison, I gained a lot of information. So for each comparison, I'm actually learning one more value in the output list. So now I'll compare 19 and 2. 2 comes before 19, so same argument. 2 comes before everything after 19. Comes after everything before 19. Comes after before everything after it. Compare 3 and 19, I know 3. Compare 4 and 19, 8 and 19. And now we reach the end of one of the lists. So there's nothing left to compare. I know 19 was compared with the last element of this list, and that element came before 19. So 19 and everything after it must not have anything to do with the rest of the other list. There's nothing left to compare. Everything here has to come after this, and everything here is already in sorted order. So just copy it all over. We can just copy that whole rest of that list in there. So what we effectively have is every time we figured out that the position of any one number in the output list, of which there are n, every time we figured out a position, we only needed at most one comparison. So if we did one comparison each time, assuming our comparator is O of 1, which it certainly should be, but not always the case, then we got our linear runtime. We did a constant amount of work for each element to figure out its position in the output list. So we've effectively merged these in O of n time. The code looks a little more complex than the merge sort itself. But there's not too much going on. There's just a bit of overhead, a little bit of bookkeeping here. We have our pointers starting at the first element, and then making the comparison. We're doing one call to the comparator, breaking ties arbitrarily with the else, and then depending on which one is coming before or after, we're going to append that to our output list and increment that pointer. And then these two loops are for if we hit the end of one of the lists, depending on which list was hit these while loops to copy the rest of the elements in the other list over to the output. So this is the only time we actually used our comparator. This comparator we were given, that merge sort was given, it passed the comparator to merge, it passes the comparator to its recursive calls. This is the only time we actually use that comparator, and that's what's going to decide how we actually order these elements. So again, we don't care what we're sorting, we don't care how we're sorting them, we're just calling this one comparator that we're given on two values from these lists of type T. We don't care what T is. We're just calling that comparator on some things we don't know what they are and deciding the sorted order based on that, based on the return values. So same idea as our selection sort. We're just being more efficient about the way we actually sort and compare these things. So let's take a look at this in action. So I'm going to sort some values, sort them by decreasing absolute value for what it's worth. And I'm going to run a little bit of timing to actually be able to see the efficiency of these things. So let me tone this down a little bit. Let's run 10,000 random doubles and sort them using Scala's built-in sort with. And the punchline will be always use the built-in sorting methods. Don't write your own sorting methods. Teams of engineers have spent decades optimizing these algorithms that are in the standard libraries. Don't bother trying to recreate what they've done. But let's see how we compare to those. So to sort 10,000 elements using Scala's built-in sort with, and then I have a little bit of timing code. I'm measuring time in nanoseconds, and then dividing them to get milliseconds. We got 23, almost 24 milliseconds to sort 10,000 elements. 10,000 is not a big number to a computer. So let's compare that with our merge sort that we saw in the slides. Same code we saw in the slides. Same merge method that we saw in the slides. Let's run this and see how we compare to 24 milliseconds. Oh, I was hoping it wouldn't be this slow. 3 seconds. Holy crap. 3 full seconds to run that. So not so great. Let's, before we talk about that, let's switch back to sort with, and let's crank this up. We did 200,000 last time. Let's really drive this point home and do 500,000. No, screw it. We're going for it. Let's go for it. Let's do 1,000,000 elements. And see how long it takes with an n log n algorithm. And by the way, selection sort, it's not even in this conversation. It would be too slow. I could show you how slow it is, but I don't want to wait that long. But 1,000,000 elements, 0.65 seconds. It's pretty quick. 1,000,000 is still a small number to a machine. This is why we use computers. It can handle these large inputs that, I mean, I could probably spend the rest of my life sorting a million doubles and never get there. This, less than a second, no big deal. So good question. See the what? Oh, it'll be, I'll go into it quick, but I don't think we'll, oh, that wasn't so bad. Arrays, that sort, yeah, maybe I'm not there yet. Tim sort, oh, that sounds familiar, yeah. Teams of engineers working for decades, they've optimized this so much, it's pretty much unreadable to us. But, it's fast, it's efficient, it's correct. That's a modified version of merge sort. Merge sort is still pretty common in practice, but they squeeze some extra optimizations out of it. So sort width took a little over half a second. 655 is our target. Let's go back to our merge sort. Obviously, I'm not going to run it as is because it's probably not going to finish before the end of lecture, almost certainly. But let's swap out merge. So with this merge algorithm, I mentioned apply is horrible. This append to the end of a linked list is a horribly inefficient algorithm operation. There's a lot of really bad stuff I'm doing in my implementation. So even though I'm getting an n log n algorithm, I'm implementing it so poorly that I don't actually get n log n runtime out of my specific implementation. But what if I was smarter? Oh my goodness, I can't click. Well, what if I was smarter about my linked lists? I'm going to use this foreshadow merge, foreshadowing some of the data structure stuff we'll talk about, where I don't make any of those mistakes, where I'm being smart about my linked list, understanding how a linked list works, and not getting those horrible runtime blowups that I was with my applies and my append to the end of a linked list. Million elements, our target is 655 milliseconds. We shouldn't expect to get 655 because I'm not teams of engineers working for decades, but we're in that conversation. We got about a little less than a 3 times blow up in runtime, 1.6 seconds. So that n log n, that's critically important. The constants, the sloppiness in my design, I mean, it's not too sloppy, but I'm just implementing vanilla merge sort as you'd see in any textbook. I'm just implementing that vanilla thing without really thinking about it. Yeah, I get a multiplication in my runtime, but not horrible. Like, I can still use this algorithm. It's not that bad. But again, use the built-in ones. Use the built-in sorting algorithms because that's going to leverage all that work that other people have done. So let's go back to this, and I want to set a breakpoint. And let's start shifting gears into this recursion, finally. Let's talk about some recursion. Runtime was fun and all, but I'll leave that to 250 at this point. But let's take a look at this recursion. I'm going to run the debugger and see what's going on with the stack and the heap and everything at this point. So the first thing I want to point out, just for what it's worth, this comparator that we have, it's a function. It's actually a class named function, an object of type function2, which is a function that takes 2 inputs for what it's worth. And we can see it does have an address. It does go on the heap. Our functions do go on the heap when we create them. So when I wrote this function, that created an object of type function2 on the heap, in this case at some 980, whatever that means, but the JVM can know where to find that on the heap. And then we have this input list of size 1,000,001 because I had an off by 1 thing when I wrote this code. So 1,000,001 doesn't affect what we're talking about. And then I'm going to make 2 recursive calls. Split this in the middle and make 2 recursive calls. The first one on the left side on 500,000 elements on this left side. So let's start stepping through this. I go into that recursive call, check if the length is less than 2. 500,000 is not less than 2, so we're going into our recursive step. splitting this in half. Debugger takes a while on 1,000,000 elements, as it turns out. Split this in half and make that recursive call on the left side of this list. So I'm going to make a recursive call on a list with 1/4 elements. I shouldn't have done 1,000,000. It's going to be a little slow to do each click. So call merge sort itself on 500,000 elements. 500,000 elements. Come on, debugger. I have faith. It's gonna do it soon. Anybody have questions while we're waiting for the debugger? Hey. All right, so now we split that list of size 500,000 into 2 lists of size 250,000 each. Let's step through one more time. Now we have another call with an input of size 250,000. And here I want to take now that we have some things going on here, I want to take a look at this stack here. So if we look at our main method, where we just called my method large example created the list, set up the runtime, and is currently waiting on this call merge sort, waiting on that line to return with a full sorted list of 1,000,001 elements with all the inputs that it was given. Merge sort, that top level call, is waiting on this call of merge sort, this recursive call. We can see all the values. It has a list of 1,000,001. It split that into 2 lists of size 500,000-ish. And it's waiting on that first recursive call to come back with a sorted list of 500,000 elements that it gave it. That made this recursive call, which is waiting on the same thing. This has an input list of 500,000, which it split into 2 halves, into 250,000 each. And then the current stack frame that we're waiting on, which has an input of 250,000 elements and is about to check if 250,000 is less than 2. I think it's going to be. That's going to split the list in half and just keep making these recursive calls of that first merge sort, merging the left half of the list. So we're just getting an input, taking the left half, making the recursive call, taking the left half, making the recursive call. And we're going to do this until we finally hit our base case, which I'm going to skip ahead in the debugger. I'm moving my breakpoint to here, so I want to stop the next time this line is hit, which is going to be when we hit our base case, and hit the resume button. That's going to get me right to that first time the base case was hit. So now we can see that we have quite a few calls on the stack. Where we left off, we had input of 250,000, went down to 1/8 million. We go down to splitting that in half, splitting that in half, splitting that in half, splitting that in half, so on and so forth, until we get down to finally an input of size 1. And we have an input size 1, and we have just one random double that I generated, 0.485, and this is where we finally had our base case, where our base case just says return. So, and we can explicitly see, I wasn't just making that number up, an input of size 1,000,000, it only took 20 levels of this recursion to get down to our base case. You take 1,000,000 divided by 2 20 times, you're down to 1. You're down to slightly less than 1 if you're punching that in a calculator. But we have our integer division, which took care of that part. So we have our input of size 1. We know what to do with that, we just return it. And now we're back. We finally are at a point where a stack frame is returning. That stack frame returns, and we're at a call where we had an input of size 3, split that into 2 inputs of size 1 and 2, and our input of size 1 just returned with that, with that sorted list, size 1, with just that one element, and stored that in left sorted. Then we make the recursive call on the right-hand side. That's going to get an input of size 2, which it splits into 2 inputs of size 1. the left returns, the right returns, and then we hit our merge. Oops, I wanted to step out of that one. So we hit our first merge. I'm not going to step through all the pointers. Watching the pointers move with just one element on each side isn't interesting. Even without that, it's not too interesting. So we finally get to this input of size, and then those two lists are merged. We finally get to this input of size 3. It has two lists. It has left sorted and right sorted, and its task is to merge those two lists, and then return those to the next step of the recursion. So then this method, this stack frame, is going to get that left sorted back with 3 elements, make its recursive call on the right-hand side, which looks like it'll have 4 elements. That'll go down the recursion, come back up the recursion, and have a sorted list of 4 elements, and now we're merging a list of 3 elements that's sorted, a list of 4 elements that's sorted. Merge those together, return those. Then there's the next recursive call, which is waiting for that list of size 7 to return. And then it's going to recursively call that on a list of size 8, wait for that to return. Once all these recursive calls finished, all these frames are put on the stack and destroyed and returned off the stack and everything. After all that's said and done, we're going to get back to this first recursive call with 2 recursive calls of 500,000-ish each that are returning, merge those 2 lists, and finally make that last recursive return back to the main, back to large example, that large example method. And I highly recommend this when you're running your recursive algorithms. Go in the debugger, look at all the stack frames, especially setting a breakpoint on your base case and running the debugger. See all those frames that were put on the stack and see what's going on inside memory with that. Or you can wait till the lab where I'm going to make you do that anyway, spoilers. But in the lab, when I say you didn't get stack and heap on learning objective 1, don't worry, there are opportunities. That's one of them. Here's a recursive method. What's going on the stack? And with immutability, what's going on the heap when we create these new immutable objects? So let's talk about writing recursive methods. So far, we've really just been looking at what they are and how they work. But let's talk about writing them, because that's the task you have for your lecture question. So here's my suggested approach, similar to how I had a suggested approach for the state pattern. Write your API, figure out what states you have, and then figure out your state transitions, and then what's the behavior of each state in for each API method. Similar to that, I have my suggested approach for recursion. First, assume that all your recursive calls are going to be correct, and write your method based on that assumption. So just say, if I had a method that does what I'm trying to do, let me just call that on a different input, obviously not the same input, or else every method would be one line, and they also wouldn't work. But call that and just assume that your recursive calls are correct while you're writing your algorithm. Then add in your base case or cases that are some trivial input-output behavior that is just going to be right. And then finally, make sure your recursive calls are always getting closer to your base case. So your recursive calls, you can't just say, recursive call on the exact input. Jesse said assume it's correct, so I'm done. No, your recursive calls have to always get closer to your base case. So in merge sort, we assumed our recursive calls are going to be correct and wrote this top level algorithm based on that assumption. If I make 2 recursive calls that are going to sort, my task is to write this merge method, which is going to merge those 2 lists and then return it. So if I do have something that can sort smaller lists, my task is to merge those smaller lists that are already sorted. So this algorithm is designed with that assumption that merge sort itself is going to work. And this is what we call, if you're here to this is what we call a divide and conquer approach. We had an input, we broke it into smaller inputs, solved those smaller inputs, and then merged them together. We divided, we conquered, and then merged those conquered subproblems. We usually don't say the merge part because it doesn't sound as cool, but we divided, we conquered, and we merged. Then we added a base case and said, okay, well, if the list is already sorted, which means it's size 1 or 0, if it's already sorted, just return it. That's our base case, and this is any trivial input, any input where the output is trivial. that can be a valid base case. That's something you want to use as a base case. And then make sure your recursive calls are getting you closer to the base case. So if I have some input, I can't solve it. I'm going to hit my recursive step here. I want to get closer to my base case. In this case, we're going to make 2 smaller lists. Since the input size got smaller for my recursive calls from my original input, I'm getting closer to that base case of a size 1 list. So I got closer to my base case in my recursive calls. So let's go through these steps a little more. That was the example that we're looking at. But let's look at these again. Assume your recursive calls are correct. This can seem tough to think about at first. It's a pretty different way of thinking, but just assume that they're correct. And if the rest of the steps line up the way you want them to, then that assumption is just going to be correct. And that's where the trick comes with recursion. That's where it can seem like magic at times, that it just kind of works. But to design your algorithm in the first place, just assume that that is going to be true, that your recursive calls will return what you expect them to return, and design the rest of your algorithm with that in mind. So like merge sort, we're going to design that merge algorithm. We're going to assume that merge sort is going to return 2 sorted lists, and then we're going to write merge with that assumption intact. Okay, if those recursive calls actually do work, what's my task? What task am I left with? And if that assumption is not correct, you probably got some work to do somewhere else. There's something else that broke along the way. Probably the design of your algorithm itself. Even with that assumption, you might have designed it wrong. Is typical. Write a base case that with a trivial input-output. These are typically like an empty list or a list of size 1 that we saw with merge sort. An empty string like we saw with the anagrams question, which we'll revisit on Friday. 0 or 1, 1 for your lecture question today. You know if your input is 1, your output is 1. You know if your input is 2, your output is 1. Those are simple cases that you can hard code into your thing. So any simple input outputs that are very easy to compute, something that you know it can't be wrong. Anyone can look at the base case and say, yeah, that is what the output should be on that case. And conditionally run your base case or your recursive case. Either you're returning a trivial solution or you're making recursive calls to get down to that trivial solution. And then finally, ensure your recursive calls always get you closer to your base case. If your base case is 1, on any input of size n, assuming we don't have negative numbers, any input of size n, better only be making recursive calls that are smaller than n, inputs of smaller than n. Always get closer to your base case. This way, when you make all those recursive calls, you're putting all those frames on the stack, you want to make sure you're eventually getting to your base case so something can return without making another recursive call. If we don't have that, if we never reach the base case, you're going to have what we call infinite recursion, similar to an infinite loop that just loops forever. You're going to get the infinite recursion, which just keeps putting frames on the stack until you run out of stack space, and you're going to get that stack overflow error. If you see stack overflow when you're writing recursive methods or recursive functions, that's the first thing to check. Is my base case being hit? Are my recursive calls always getting me closer to my base case? And in some cases, are my recursive calls skipping right over my base case? Maybe I'm always subtracting by 2, my base case is only 1, and my input is 2, and I'm skipping right over it and going to 0, and then going to negative values. That can also be an issue. And for strings, for the anagrams, we were always removing a character from the string, getting us closer to that empty string. To be able to get that trivial return, actually string of 1 character, just return it. It is its own anagram. Any questions on all this? Yes?
What if you overflow the stack before like a base case is reached, like you said, recursive calls?
It breaks. So if you overflow the stack before hitting your recursive, your base case, yeah, it breaks. So the idea with recursion is you shouldn't be using that much stack space. You should have these like logarithmic breakdowns. Like for merge sort, with an input of 1,000,000, we only had 20 frames on the stack at any given time, which isn't close enough to overflow our stack. So if our algorithm is in danger of overflowing the stack, we should be rethinking our whole approach. That said, for the lecture question, you might overflow the stack with high inputs, but I'm not testing on large inputs. So that's not a concern for the lecture question. In practice, you wouldn't write this Fibonacci thing recursively. All right, I'll see everyone Friday.